Questions about anything last time? Or anything? Oh, I thought I'd slow down today and start talking about integrable functions on the real line, because the Fourier transform is defined in terms of an integral from minus infinity to plus infinity. And we haven't exactly reviewed the basic facts of calculus when you're integrating on an infinite interval. I should mention this. This is kind of reminiscent of some calculus facts. The theory of integration on from 0 to infinity, for example, is very similar to some calculus facts about series. A series summation un, then goes, say, from 1 to infinity. We say that it converges absolutely if the sum of the absolute values that was a definition. And then it's a lemma that if a series converges absolutely, it converges. A series that converges so it doesn't sound like it ought to be a theorem because it says that an absolutely convergent theorem series converges. But the definition doesn't say that the thing converges. It's a consequence of that condition. So a series that converges absolutely converges. Sounds silly. Okay, so, and the fact when we're talking about integration is going to be, let's see, for now, the why we did this was this series as n equals, goes from 1 to capital N of the un is non-decreasing. So if it's bounded above, then it has a limit. I'm sorry, what is it? I call it increasing, but fancier word maybe is non-decreasing. If it's bounded above, it has a limit. It has a limit L. And then once we know that fact, then we can show that the partial sums, if sum of the un is absolutely convergent, then you can show that the partial sums form a Cauchy sequence. Then S capital N, which would be the sum from 1 to capital N, is a Cauchy sequence. And so it converges. Because that was the completeness of the real numbers, is that Cauchy sequences converge. That was the completeness of the real numbers. Okay, so we're doing something similar here with integrals. So, well, let's see. Another fact about series. If a series converges, then the terms have to go to 0. And of course, not the reverse. Now, the terms go to 0 as n goes to infinity. That was a pretty easy thing. The y in freshman calculus is you write S sub n is the sum from 1 to capital N of un. And then if I were to take S of n minus S sub n minus 1, that would be U sub n. And if these are both, then as capital N goes to infinity, this partial sum would tend to L, and so would this one. And so that means the terms U sub n go to 0. So that's all there is to that. Well, this is the fact I was talking about in Piazza about the last homework. So when we're talking about integrals, which are kind of like an infinite integral is kind of like an infinite sum. Notice that, let's suppose I have f is continuous on the whole real line. Then if I were to integrate the absolute value, so I'll go from 0 to b dx is a non-decreasing function of b. So it either goes to infinity as b goes to infinity, or it's bounded above, and therefore it would have a limit. So it's non-decreasing in b. It either goes off to infinity, either the integral from 0 to b of f dz goes to plus infinity as b goes to infinity, or it's bounded above. Bounded in b. In which case it has a limit. So you would let the limit be the least upper bound. That's called the soup. That's equal to the least upper bound. Then L is equal to the limit. That L would be the limit as b goes to infinity of integral from 0 to b of the absolute value of f dx. Okay, and in this case we say that f is absolutely integrable. So the definition, if that L is finite, we say f is absolutely integrable on at least the right half. And we write integral from 0 to infinity of absolute f dx is equal to that limit. And here's something kind of like that series fact that you needed in the last homework and that I reminded you about on Piazza. If f is absolutely integrable, then the tail end of that integral has to go to 0. If f is absolutely integrable, on 0 infinity, then the tail end of that integral has to go to 0. Then the limit as b goes to infinity of the integral from b to infinity of f dz equals 0. So the tail ends sort of eventually have negligible contribution to that integral, kind of like the tail end of a series. And the reason why is, let's see, I talked about it. What did I like to do? Okay. The integral from 0 to infinity of absolute f dx, that would be equal to the integral from 0 to b of f dx plus the integral from b to infinity of absolute f dx. Okay, this is that number L we were talking about, and this number is increasing to L. As b goes to infinity. I'm letting b go to infinity here, and it's like the tail end of the series. If that's increasing to L, then this has to be going to 0, decreasing to 0. That's all there is to that. And to see that this is that fact that if f is absolutely integral, then the limit as b goes to infinity of an integral from 0 to b of f dx exists. And the basic estimate is that comes from looking at the tail end of the integral, and you'd have the estimate that the integral from b to infinity of f dx, the absolute value of that thing, is less than or equal to the integral of the absolute value. When you have that estimate for finite intervals, you easily get it for infinite ones. Okay, so those are the review facts I wanted to get out of the way. It's surprising you can use that. Let's see, I guess that homework problem is a key example. In homework 7, problem 1. Let's see. It was to prove sort of the Riemann-Lebesgue lemma. C1 smooth absolutely integrable functions that's stronger than you need to prove the Riemann-Lebesgue lemma, but you can get an elementary proof in this case. So C1 smooth absolutely integrable functions on R. Oh, I didn't say what I meant. So here's absolutely integrable on R means it's absolutely integrable from 0 to infinity and from minus infinity to 0. So an F is absolutely integrable on R means it is on the left side and the right side. And that means you don't have to sweat about anything at the tail end. We would write the integral from minus infinity to infinity of f dx. You can write that as a limit. It doesn't matter how the rate is, as a goes to minus infinity and b goes to plus infinity of the integral from a to b f dx. I guess the right way to say it would be at the integral from minus infinity to 0 of f dx plus the integral from 0 to infinity of f dx. And when you put those together, it doesn't matter what rate you let these things go to minus infinity and plus infinity. Okay, so let's put, if I call that function something, prove the Riemann-Lebesgue lemma for C1 absolutely integrable functions. Let me call it F. Okay, so the Riemann-Lebesgue lemma is like a Fourier series thing. Namely, that was that the Fourier series tend to 0. Coefficients tend to 0. And what is the Riemann-Lebesgue lemma in the context of the Fourier transform? We'd have this integral of things like, let's see, I have f of x sine wx from minus infinity to infinity. Or cosine x, or cosine wx. Or e to the ix, because e to the ix is just cosine wx plus sine wx. And so the Riemann-Lebesgue lemma you think of it as wiggling. As the w goes to infinity, the sign wiggles more and more. And the wiggling causes cancellation. And so even though that integral doesn't look like it should be going to 0, it's the wiggling and the cancellation that makes it go to 0. Or minus infinity, but they're the same. Since sine of minus something is minus sine of it. Okay, so that's what it's about. It's about the canceling business that we used in the Fourier series argument. And so the key to that argument was to realize that the tail ends become negligible when you start thinking about this. So the solution to this problem that I gave you in the, I don't think I posted solutions yet. But I want to talk about this before I post it. Let epsilon be bigger than 0. Then the tail end of that series becomes negligible. Then there is an n such that the tail end of the series with an absolute f in there, so that would be the integral from n to infinity of absolute f dx. Let's make it be less than epsilon over 3. And I want the other n to also be, so I want minus infinity to minus n also to be less than epsilon over 3. So I can choose an n that's big enough so that both of those happen. So there's an n such that blah. That's true. Because those things tend to 0 as n goes to infinity. Okay, and so I can make the and notice that the if I put a sign in there, so important, that I'll just do one of the n's. The integral from n to infinity, for example, of f sine wx would be less than or equal to the absolute value, the integral of the absolute value and of course the absolute value of the sine wx is less than or equal to 1. So that would be less than or equal to the integral from n to infinity of absolute f dx. That's less than epsilon over 3. And same for the other end. Same for the minus infinity to minus n side. And once you have that fact, then now that you fix the n, and then you look at the middle integral. So fix the n and use integration by parts. To bound the integral from the middle part. Let's see, f of x sine wx dx by something, a constant, divided by n. And the key to that is when you use integration by parts, this is going to be the dv, this is going to be the u, and when you do the integration by parts, the v is going to be a 1 over w. Oh, let's see, constant. I'm dividing, this is going to be over w. And where does the 1 over w come from? When I do integration by parts, the v would be minus 1 over w cosine wx. And that's exactly what gives you the w when you write it all out and look at it. And of course, you've got bounded, f and f prime would be bounded on that integral. And the sine and the cosine are bounded by 1. since f and f prime continuous on that closed interval minus n implies they're bounded. So that's where you'll get the constant from. So that's an important tool in using sort of so you can ignore the tail ends of those integrals. There's a problem this week where that would be relevant. Number 1. So that's a hint. Similar idea for the problem 1 in homework 8. For homework 8, problem 1. Once you've seen it once, it gets easier. Oh, let's see. Well, now I want to go and talk a little bit, at least, about the stuff Stein. So Stein's book, page 134 to 144, demonstrates Fourier inversion, and it's kind of mind-blowing because he does it so efficiently. The Fourier inversion formula. And I decided I don't want to get too carried away with the nitty-gritty details. I just want to give you the key facts of why this is a true thing, so you can understand where the heck this crazy thing comes from and why it's not as surprising as maybe you would think it is. And so to get ready to do it, Stein starts talking about functions of moderate decrease. So this is an exclamation point because it's kind of mind-blowing that he could do that. And so he starts out by talking about a space of functions called M on R. These are functions of moderate decrease. This is kind of the type of functions engineers and scientists want to apply the Fourier transform to. Functions of moderate decrease on R. So that's decrease at infinity. And they're the functions f, such that f is continuous on R, such that they decay at infinity at a certain rate, such that absolute f of x is less than or equal to a constant times 1 over 1 plus x squared. When absolute x is bigger than m. So the tail end decays that fast for some c bigger than 0 and m bigger than 0. It's kind of a mouthful. Well, the thing to note, the reason these are chosen is it's very easy to calculate the tail end of that integral. The integral from 0 to infinity of 1 over 1 plus x squared dx. That's the famous, has an antiderivative of the arctangent. So the fundamental theorem of calculus would say that's the limit as b goes to infinity of the inverse tangent of x evaluated between 0 and b. And the inverse tangent, you take the graph of the tangent function and you flip it twice, and you get the inverse tangent, and it looks like this. So that's the graph of the inverse tangent of x, and this is pi over 2 and minus pi over 2. And so that limit is pi over 2 minus 0. And so it's finite. So if a function is squeezed under that by a constant, then of course those integrals all exist, the infinite integrals. And here's the basic facts we need to get going on Fourier transform. Let's see. Number one, if I take a function and send it to its integral, that's a linear operator. So it's a linear operator mapping moderately decreasing functions into the real line. That's because of the integral. Integrals on finite intervals do that, and so in the limits, of course, those will be also true. I'm not going to write out proofs of these because it'll bore you to death, or at least not all of them. Here's an interesting one. Integral from minus infinity, if I shift a function, x plus h. If I'm integrating over an infinite interval, shifting it doesn't have an effect. It just picks up an infinite thing and moves it a couple inches to the left or right. And so that's an easy thing to do with a change of variables. You'd let this be a u, and then of course du is equal to dx. And I take it on a finite interval and let the limits go to infinity and see, sure enough, it's just a change of variable formula. Do it on a finite interval and then realize that you can let the limits go to infinity, minus infinity and plus infinity, and get the result. And a similar thing is if I scale, so that one's a shift, this is a scale. So let's see, if I scale a function, what is that going to do to the integral? Let me think about it for a second. Equals, I claim it's going to, I'm going to think about this for a second. I kind of want to write f of u here instead of f of x. There's a blank there for a good reason. So if I were going to do the similar thing here, I would let u be equal to kx. And then, let's see, dx, u is equal to kx. And so du would be equal to k dx. And so when I realize, oh, my dx is 1 over k du. And so what goes here is a 1 over k. And similar thing about thinking about the limits. I'd go from minus a to plus a, but then when I do the scale, it would scale the limits But then when I let a go to infinity, those integrals would be infinite extent. So that's a pretty straightforward thing to do. So it's a change of variables formula here, too. That's kind of a simple thing to do.
Why isn't it k times? Because if you replace kx with u, then
Let's see, I'm going to have a u there, and I got to change my dx to a du. And when I change my dx,
it's like f of u times du.
yeah, so my dx would be a 1 over k times du. And then I'd stick the 1 over k in front and do and that would spit it out, I believe. Okay, the only one I'm going to demonstrate is the last one, which is maybe, and we're going to want to differentiate these things. We're going to have difference quotients in a derivative, and of course the numerator is going to look like this. And you kind of know that differentiable functions are continuous. But this is kind of in the same vein. But the fact is, if you have a moderately decreasing function, then this goes to 0 as h goes to 0. So 4 is the only one that requires a little bit of thought. And it's going to be similar to the example I did starting out here. If I give you an epsilon bigger than 0, I want to make the tail ends negligible. So all I have to think about is on a compact interval. And in a compact interval, I've got uniform continuity. That's going to be the key. So let's see. Given epsilon bigger than 0, there exists an r bigger than 0, such that the tail end of the integral of f is as small as I want it. So let's see. I'm going to make the integral of absolute f let's see, absolute f dx. I'll go from, I'm thinking about what I'm going to put here. I'm going to put r minus 1 because I might want more. Is less than epsilon, oh what? How about epsilon over 4? And the other end too. So let's see, the other end would be the integral from minus infinity to infinity, let's see, r minus 1. Minus r plus 1, how about? So in other words, the tail ends are small, and I stick in a plus 1. I'll tell you why I want to do that plus 1 there, because h is annoying here. So I'm going to assume, I want to take a limit as h goes to 0, so I'm going to assume that absolute h is less than 1 at least, before I let it go to 0. Okay, well it turns out now I can estimate the whole thing. The integral from minus infinity of f of x plus h minus f of x dx. Okay, that's equal to an integral from minus infinity to minus r plus the integral from minus r to plus r plus the integral from r to infinity. Okay, this one is the one we can use uniform continuity. So here I'm going to use uniform continuity. Of f on, so it's continuous in a closed interval. So, and I'd make it from minus r minus 1 to r plus, no, I want to make it slightly bigger interval. Minus r minus 1 to r plus 1. R minus, yeah. Yeah. Then it doesn't matter that one of those, that h is kind of sticking out one of the ends. F of x plus h would be sticking out one of the ends. So you don't have to worry about that. The uniform continuity means if h is less than delta, then that thing inside the integral is less than epsilon. I'm going to make that small enough. This less than, I guess epsilon over 3 would have been enough. Oh, I guess I should be careful. I want to make f of x plus h minus f of x less than, how about epsilon over 4 divided by 2 times r plus 1? Let's see. What's the length of that thing? It'd be 2 times r plus 2. When h is less than delta. Okay, that's the key. And the other ones are going to be easy to bound. Let me do one of them. The other two are easy to bound by epsilon over 4. Let me do one of them. Let's see, the one, this one, integral from r to infinity of f of x plus h minus f of x dx. That would be less than or equal to the integral from r to infinity of f of x plus h dx plus the integral from r to infinity of absolute f of x dx. And this would be less than the integral from r minus 1 to infinity of absolute f dx. Because of the shift. When I do the shift, h is less than 1 in absolute value. So if I shifted it by a little bit, that one would be less than that. And this one's less than epsilon over 4. This would be less than it too. And these are both less than epsilon over 4. Oops, I should have made it less than epsilon over 5. 1, 2, yeah, I've got 5 of these stupid things. So this one's less than epsilon over 4. This one's less than epsilon over 4. And so I get 5/4 times epsilon. Now you go back and replace the 4 with a 5. Okay. Well, let's see. If you Google Fourier transform, and look at the Wikipedia article about it. You'll see that there's multiple definitions of the thing, which is kind of annoying. So one definition of the Fourier transform puts f of x, puts the e to the minus I 2 pi sx right here. And then the inverse Fourier transform, when you use this version, is equal to integral from minus infinity to infinity of you take the f1 version of the Fourier transform, and then the inverse is nice in that it's got a plus 2 pi in the same spot. This one's going to be the preferred Fourier transform when we do anything theoretical. But the engineers prefer this one. So this is the preferred, Stein prefers this for theory. Because the theory, and I'll explain why the theory becomes easier to write out next time. The F2 version is preferred by engineers, maybe, because of its relation to the Fourier cosine and sine transforms. This one's kind of easy to remember because these look very much the same. And the only difference here would be an e to the I plus s, sx ds. And then the last one, of course, these are all really exactly the same thing. It's just that the darn 2 pi pops up in different places. If you know one of these things, you know them all. And then when you do the inverse, the 2 pi pops up here.